Hi, this is Ana Douglas with the first video of the module Geometrical and Ray Optics of ECE 513 Intro to Optics and Photonics. In this video, we will introduce light beams as rays. We will talk about the refractive index and the Snell law, which provides a quantitative description of ray bending when light travels between two media of constant refractive index. So in ray optics, geometrical optics, there are four postulates. The first postulate is about how we understand light. So we understand that light is going to be composed with rays. So those rays are emitted by light sources. They are reflected by mirror or transferred through lenses until they reach at the end an optical detector. The second postulate is related with how we're gonna characterize a medium. So when we are thinking about mediums, we're gonna use a parameter that is the refractive index. So the refractive index is gonna be related with it's gonna give us a quantitative description about how fast the light travels on the medium. So it's the ratio between the speed of the light in free space or vacuum. That's a universal constant, so it's already known, and the speed of the light on the medium. Because light cannot travel faster than in the free space, then the refractive index is gonna be higher or equal than 1, and this is a hard limit. So if you have ever get a value of the refractive index lower than 1, that usually means that the ratio that you have used is B over C instead of C over B. The third postulate is related about how the light travels. So in general, when we have a medium, we're gonna assume that the refractive index is gonna be a function of the 3D space. So this is gonna be 3D space. That is gonna be, in this case, given by the rectangular coordinates. So if we have a point A and light needs to travel from A to B, we're gonna it can travel to this path, for example. We're gonna define the optical path length as the integral through the path from A to B. That is the product of the refractive index, that, remember, it's a function of the space, and then the differential element of length along the path. So this is gonna be our differential of the length along the path. So the Fermat postulate, this is telling us how the light actually travels. So again, we have from A to B, but ideally there are so many paths to reach, right? So I'm just gonna make here like a straight line or even some kind of parabolic or quadratic path, but we know that the derivative of the optical path length are around the element unit along the path, that's gonna be 0, right? So that tells us that light travels from A to B in following a path with derivative along the unit is gonna be, the optical path length derivative is gonna be 0. And that imposes some conditions of the optical path length. So that means that the optical path length can be minimum, maximum, or a point of inflection. So there is this particular case, which is the first rule in optics, that it tells us that if we have from A to B, and now the refractive index is constant, so that's not changed, it's not a function of the space, then the light travels as a straight ray. So that means that the optical path length, it's minimum when the refractive index of the medium is constant. So rays are straight lines. And this is key for geometrical and ray optics because this is the basis of everything. So when we are defining the optical path length, right, and we remember that is from point A to B, the refractive index multiplied by the differential of the length. Now that the refractive index is constant, we can put it outside of the integral. So here we're gonna have our differential of length. So this is because Cn is constant, but now this integral right here, this is gonna be my geometrical distance from A to B. And that's how we usually gonna define more the optical path length. So thinking about optical, the other rule, it's about what is gonna happen when a ray emitting from a point P meets a mirror, right? And we know that from P to the mirror is gonna follow a straight line, and then because it's gonna meet a planar mirror, light is gonna get reflected, so it's travel from P to the mirror to O, and then from O to Q, this is our reflected ray in such a way that we know that the incidence angle is gonna be equal to the reflected angle. So every time the light reflects, the angle with respect to the normal needs to be exactly the same. The other rule is related how the light acts when we meet an interface. So when there is a change of the refractive index, so we move, for example, from air to water, right? So light travels through a refractive index A1, and we have like a theta 1. This is my incident ray, and theta 1, this is gonna be my incidence angle. And then it's gonna meet an interface, and then we're gonna have a refracted ray. So when light travels with media of two different refractive index, we know that the product between the refractive index and the sine of the angle with respect to the normal, this is gonna be constant. So knowing that this is gonna be constant, we can estimate the angle of the refracted ray as the inverse of the sine of n1 over n2 sine of the incidence angle. So we're gonna talk more. So here, based on the relationship of n1 and 2, we can talk about external refraction or internal refraction. So in the class number 3 is gonna be related with external and internal refraction. What is gonna be related with the relationship between n1 and n2. So now that we have introduced the Snell law, let's do two examples. So the first example is, let's assume that light that travels in air approaches the boundary of oil. All right, so, and then we know that the incidence angle is 36.1 degrees with respect to the normal, and the light travels at the speed of 2.27 multiplied 10 power 8 through the oil, and they want us to estimate the refraction, the refracted angle. All right, so let's do the problem. So we have here our interface, and we have here air, and this is oil. So the air we know that the refractive index of the air, this is 1, and the refractive index of the oil, we don't know it, but we know that this is going to be C over V2, right? And they told us that V2 is 2.27 multiplied power of 8. Alright, so let's define the normal of the surface. And now we know that we have an incident angle θ1 equal 36.1, and we know to estimate our θ2. So we can use our Snell law, so we know n1 sine of θ1 is going to be equal to n2 sine of θ2. Again, θ2 is going to be the inverse of the sine n1 over n2 sine θ1. And originally we have everything because n1 is 1, n2 we can do a C over V2, so this is gonna be 1.32, and then θ1 is gonna be 36.1. So we can see here that the inverse of the sine is gonna be 1 over 1.32 sine of 36.1, and the result is 26.1 degree. The other problem is a little more complicated, just a little bit. So the difference of the other one is like instead of having one interface, I have two interfaces, kind of like in cascade. So light travels from air to water with an incident angle of 48.2, and then from the water we have another interface going into oil, and they want us to estimate the angle of refraction from the air water and then from the water oil. So you can do this as like in cascade. So the first problem is gonna be, this is our normal, this is our θ1, and this is gonna be our θ2. So we're gonna say n1 sine θ1 is equal n2 sine of θ2, and we know that the refractive index of the water is 1.33, and then we know that the refractive index of the oil is 1.5. So θ2 is equal, and then the air is 1. So θ2 is the inverse of the tangent of the refractive index of the water divided 1.33 sine of 48.2, and this is gonna be 34.09 degrees. So now we have here our second interface. Let me try to put a different color for the second one. So let's use this green. And the light, we travel through a straight line, right? So this ray kind of propagates, and then we meet the second interface, and we're gonna have a different ray that's gonna be θ3. So the first thing that we need to check is the incident angle. So this kind of angle right here, right? So the incident angle, that angle becomes again θ2 because it's the same angle through the normal. So in the second interface, what we have is we have n2 sine of θ2 that's gonna be equal to the refractive index of the oil sine θ3. And we have two different ways of solving. The first way is just getting the results from the previous application of the Snell law. So we know that θ3 is gonna be the inverse of the sine of n3 over n2. Sorry, I meant to change the color. Over n2 sine of theta 2. And if we plug all the values here, right, we know that here n3 is 1.5, and then we know that n2 is 1.33, and theta 2 is, we just go before, 34.09 degrees. So now the angle is gonna be 29.8 degrees. The other way of solving it is just, we say that n2, if we look to the Snell law in the second interface, we know that n2 is equal to sine of theta 2, right? But what we were saying when we were applying the Snell law on the first interface, that was equal to n1 sine of theta 1, right? So we can use the incident angles in the boundary of the air and link it to the refracted angle in the oil to just estimate theta 3 as the inverse of the sine of n3 over n1 sine of theta 1. And if we do that one, then we're just gonna use all the original values, and then the result is again 29.8 degrees. Preferences: both ways, both methods are accurate. I a lot of time like more the second approach because it has less likelihood to propagate error. So that means that, let's say that you make an error getting theta 2, right? If you have an error in theta 2, then the error is getting propagated in theta 3. But if you use the incident angle of the first medium of the error, you are not propagating an error. Nonetheless, I like this because it's a way of checking results. So when you are in an exam or when you are submitting homework, you can always do check-ins with your work. This is an easy check-in, verifying that both results are the same. Well, thank you.